Okay, well, I'm going to tell you a little bit about our work that we've done in Montana over the last 6 years of having experiments in fields. Clearly, the picture in the background shows you one of Chuck's fields and how nicely some of those experiments can show up. A very important point, this came up yesterday, I mean, for us, is keeping the focus on this, increasing the farmer knowledge, not on providing deterministic prescriptions. So the whole idea is that we're trying to aid farmers in understanding their system. And so that's a primary focus. So a whole lot of things that are part of that focus. Agroecology has taught us that every field is likely to respond to management differently. And therefore, and I say this to my students constantly, ecology is site-specific, time-specific, and history-specific. And we've got to keep that in mind. And with that, as we back off on inputs, which tend to suppress the variation in the system and make them more predictable, which has been sort of the aim of our land grant system and our approach to agronomy in the U.S., as we back those things off, we have to replace that with knowledge in order to decrease that uncertainty, or at least quantify that uncertainty. So decision support directly at farmers must be based on field-specific data, or must be directed at farmers, must be based on field-specific data, informing each manager independently about each field. About each field. The experiment tells us about how that field is going to perform. So the idea is that every field needs to be thought of differently. It's not that we can't use the information. We can use the information, but we're not going to be nearly as certain. Sites use information from adjacent fields. Site-specific on-field experimentation will most efficiently deliver knowledge appropriate for decision support. Adoption of new recommended agronomic practices has been reliant upon the inefficient trial and error approach that is increasingly challenged by increases in farm size. Our farms are getting bigger throughout most of the U.S., and certainly the commodity crops. So how do we help farmers? How do we build the tools for them to understand their system better? We have access to far more data on field agronomic performance and within field variability than ever before. Can we use that wisely? We have unprecedented ability through modern analytics to characterize and predict field performance at subfield scales. So we really can be site-specific in our management. Crucial is our attention to how we condense and deliver the information to farmers if we intend to keep the culture in agriculture and not strictly be on this trajectory towards agro-automation. So, field-specific precision agriculture-based experimentation demonstrates field-to-field and year-to-year variation. So we're moving past the trial and error period. We're actually putting science into our understanding. Uncertainties in agricultural production necessitate detailed knowledge of the efficiency of production within each field to achieve future goals. Generally, our conclusions are that wheat yield and grain protein content responses to variable nitrogen fertilizer varied between fields and across years over 6 years of on-field experimentation. The covariate drivers of crop production quality and farmer net returns differed between fields even when those fields were adjacent to each other, farmed by the same farmer. But because they have different histories, they react differently. Decision support systems should be designed to be parameterized on each field with on-field experimentation. We can do that now. We have the technologies in place to be able to do those kinds of things. Okay, so we have access to more data than we've ever had. We have all these satellites flying around. We have so much information coming off of the field that we need to be very effective at how we utilize those to get at understanding our systems. So the framework that we've used, and you've seen various versions of this. This is one that Paul Hegedus developed. And the idea is that we start with an experimentation, and we might use previous information to lay out that experiment, but for particular input, in our case, we've used nitrogen management as our proof of concept here. But it could be weed management, it could be management of really any input, seeding rates, etc. That information is laid out in an experiment. that's generated based on previous response of that field. So we might put specific treatments in specific areas of the field, collect on-farm and open source data from the combine. This is a yield map and a protein map. We aggregate that data with all the other layers of data that we can get from the internet, basically. We then analyze that data against our input level to see what kind of response we get, develop the predictive models that lay the red dots on top of the black dots or blue dots on top of the black dots for yield and then protein. All the while, you'll notice that all these pieces of information are going into a database that gets managed. Very important aspect here. Once we have those modeled responses and we have them over time, we can start to simulate what the possible outcomes are, a range of outcomes that we might expect. And that's becomes a very, that's where we really make intelligent use of all that information, because we can kind of say, what are the possibilities of outcomes? From that, we can generate the highest probability of outcome map for the next year, or a particular year that we think it might be, because we're always making decisions ahead of time when we can't see can't see into the future what the weather's going to be like. So that's part of how we structure what our recommendations come from. And then we evaluate the recommendations, come up with a new experiment, and the cycle starts again. So it's adaptive management. It's a cycle of information flow. Specifically in Montana, we have farms now in different environments across the state. This is mean annual precipitation for over a 30-year period. And we have these farms that have various different kinds of rotations, and different field sizes, et cetera. And some are on with the same farmer or on the same farm and different fields. And you can see that we have more or less a focus on winter wheat here has been, again, our proof of concept crop that we've been working with. So we have data over space and over time. We can understand spatial variability. We can understand temporal variability. We get an as-applied map from an experiment that gets laid out. And we take that information that comes then from the yield monitor and the protein sensor. We couple it with all this information coming off of the internet. Sources are listed here. A whole lot of things from geographic features to responses from satellites primarily, with a focus that we've always kept. We've limited ourselves or constrained ourselves to using data that's freely available. Now I'm going to talk a little bit later about some extra data that we've used to look into nitrogen management. But for now, let's just assume that our work is primarily focused on this idea that we want to keep it as cheap as possible for the producer or for the land manager. Build these predictive equations. Again, this is yield, nitrogen rates. See this scatter that we get across this system. The lines in that data are basically those points at which we have set the rate, but the rate can vary a little bit. So we get this total scatter. We make a predictive model, which we show with a single blue line here, which isn't very meaningful because it's multidimensional. So the actual way to show the predicted values are with the red dots. And in this case, protein, the blue dots are showing the predicted levels. So we're doing okay. We're kind of covering the scatter with our different kinds of approaches. And I'm not going to go into the analytics of that. I don't think that's important for this meeting. But I'm happy to answer some of those questions. And better yet, when Paul talks a little later, he can tell you about all the juicy details. Ultimately, what we come up with is doing simulations with this work that basically shows what are the possible range of outcomes. And you can see there's a broad band, and it's showing you kind of that running mean through that. But the idea is to find those points where we maximize that estimated net return, and that would be the nitrogen rate that we might select. But we do this for every point in the field. We either divide the field up into 10 meter by 10 meter grid, or actually try to predict on every yield point that we have for the field, the tens of thousands per field in a 100-acre field. So how does that work? For each point, we're predicting basically what this net return curve looks like, given that nitrogen fertilizer rate. So for we create a curve for every single point or every single cell in the field. We find out what that maximized net return is, becomes the optimum nitrogen rate. And then we draw on data from previous years where we have the price variation for previous years. We have the cost of the nitrogen, how it varied every year, the precipitation in different parts of the year. All of these things are used then to predict what those yields might be, because over the years that we've done it, which are in the more recent years down below the black box here, we can go and start to select from that history and grab different years, and we can either do that at random, we can use them all, or we can use specific ones. So we might say, hey, this is looking a lot like 2005 or 2004. So we'll go with that year to make our prediction for what we should do in the current year. So that's how that works. So this curve wobbles it up and down and to left and right, and with different annual base prices and protein premiums, creating a distribution of optimum nitrogen rates from which probability of maximizing net return can be calculated for each optimum N rate. So we're creating this distribution. And David showed a really nice graph of that yesterday, of kind of conceptualizing that these are distributions. So what we've done is say, what are the possible ways, or what are the kinds of things that we can demonstrate in terms of the approach to managing our nitrogen, whether it be, let's not put any nitrogen on, let's use what the farmer would have selected as a uniform rate across the field. Let's use what the site-specific optimum would be. That's based on our analysis that we just did. A full field optimum. In other words, what we're going to do is uniformly apply nitrogen across the field in a uniform way. What actually happened given the experiment in the field. So this is kind of the cost of having an experiment in the field. And then some alternative price approach. And in our area, what we've started doing was comparing to what if you were getting an organic premium, with the assumption, and we let the farmer set the assumption of what the impact of weeds would be in that system. And usually it's much higher than we would think it would be. But nonetheless, we let them decide for themselves what it would be on their system. What we end up with is these distributions, which look like, gee, they don't overlap much. You know, the only one is the actual where you're really getting penalized, maybe. But the fact is, keep in mind that for each run of the simulation, we actually have one data point that we're pulling out of these. And so what we want to know is what's the probability that each one is different from the site-specific optimum. So if we do the net return of the site-specific optimum, what's the probability that the net return is going to be greater, the average net return is going to be greater than the net return minimum? So, for the minimum nitrogen application, which would be the zero rate. Well, it says 100% of the time, site-specific is going to be better. That kind of makes sense. Is it better than the farmer selected? 100% of the time, we've been better. Doesn't matter what year, what field, we've been better than what the farmer was selecting. It's not that his information is bad. It's just that when they make a decision, they're often not thinking net return. They're usually thinking maximizing yield. And that's been an issue. But this is really, I think, enlightening from that point of view. Is site-specific better than the full field optimum? Now we're using the models to say what would be the best uniform rate across the whole field. Yeah. No, we're just saying what would you put on the field this year, given everything you know? One advantage, I should have said that we're working with top dress nitrogen in the winter wheat system. One advantage in this system, of course, is that they've seen how the crop's growing halfway through before they apply in the spring. So in other words, it's been growing since the fall. So there is some advantage, and they are using that knowledge, of course, to select what that rate would be. So thanks for bringing that up and reminding me that I should have said that. So the net return, the full field optimum only 25% of the time was the site specific better than just a uniform rate across the field. So across all of our fields, all of our years. That was a bit of a surprise, actually. So site specific, it pays sometimes, but not always. And it kind of depends on situations. One thing that's a major effect here is we had 2 really dry years out of those 6 years. And the recommendation was put 0 on in the site specific. So you're never better than a full field 0 because you don't make up enough because there's only a few places where it's calling for putting the fertilizer on under the site specific approach. Does that make sense? Do you hear what I'm saying there? Puzzling looks. It's a little complicated to think that through, but anyway, then 100% of the time the site specific was better than the actual, i.e. from doing the experimentation in the field. And then the site specific optimum was only 16% of the time was better than if you were going organic. What that doesn't include is any time horizon that it takes to become organic. In other words, to get that certification, that 3-year period. Yeah. Oh, I think site specific would be better 80% of the time. Yeah. Yeah, that was, in fact, we've done that and it's pretty distinctive. I don't remember the exact number, but yeah. Big impact. Okay. So if we actually take dry years versus average years versus wet years, which is what we're looking at, on average, the site specific does better than the no nitrogen applied, the farmer selected, the model selected full field optimum was 100% on an average year. And then always better than the actual. Organics still did pretty well. Under a wet year condition, you'll notice that the full field uniform was about 50% of the time. It did just as well or better than the site specific. But it was interesting that 100% of the time it was better to use site specific nitrogen application than be organic. Okay, even though the organic is about 5 times the price. So that you're receiving per bushel. Okay. So one of the things, though, that we started out with, and the project that really the graduate student, Paul Hegedus, was most interested in, was the idea that can we use this information to come up with the trade-off between minimizing nitrogen but maximizing net return? And can we quantify what that trade-off is, what that actual cost might be to find that point? So he used nitrogen use efficiency, and it was predicted at every 10 by 10 meter grid cell. Efficiency was modeled using a support vector regression model developed from intensive soil and plant tissue sampling. So he went through the field and sampled all these tissues and things. Yeah. Oh, can I repeat that? Oh, I'm sorry. Yeah. Chuck, the question was, how impactful were those 2 dry years on our result that the full field uniform performed better than the site specific optimum? So that's where the answer that in fact, when we actually used actual years, an average wet or dry, if we were in a wet year, it was 100% of the time it was better, or the average year, it was 100% of the time it was better. So hopefully you got that. Okay, so did this over a couple of years, ecological and biochemical variants of the nitrogen use efficiency. So we were actually modeling that nitrogen use efficiency by basically determining where's the nitrogen. Is it in the plant? Is it in the soil? Doing all those comparisons at each point in the field and then developing a model on that. The optimum nitrogen fertilizer rate for any given point in the field was then identified as the rate that maximized profit while considering the cost of nitrogen inefficiency. So we did 1 minus nitrogen use efficiency because we want to know how we're losing it. It's inefficiency. And then that was what we used as the measure. I think it's easier to see with this graphic. So the idea is that you have, as nitrogen fertilizer rate occurs, and this is just a theoretical, basically a hypothetical model, then in fact we'll see the cost of inefficiency will go up as you increase that rate. And the net return, of course, goes up and comes down. And what we want to do is maximize the distance between the two curves. That's a real simplistic way of looking at an optimization, but it's because it keeps it all in a dollars and cents sort of metric. What that ends up looking like when we actually do the simulations through a field, then we get these kinds of simulation responses that look like this, where the inefficiency is the purple line and the net return is the green dots, and we keep track of that throughout the field so that we know what that variation is looking like. And ultimately what that does is suggest site-specific kinds of outcomes that allow us to say, where do we get that optimum nitrogen rates across a field for an average precipitation year, a low precipitation year, and a high precipitation year. And you can see the red areas are where it's very low. We're calling for zero nitrogen. And the green is up to the higher levels. Those are different scales, but in this one, it's 110 pounds, 124, 157. For those of you in the corn region, these all look really low, but this would be typical for wheat production in our area. So it gives you a sense of what that variability looks like, and we can then calculate what that optimum would be. But now we want to know really what's the cost of that. So the difference in net return for the site-specific optimum minus the zero rate, it gives you that. So you're going to make more money using the site-specific optimum. You're making more money than the farmer would have for the farmer selected. So in other words, it's still working for you, even though you're using that optimum. It's not costing you a lot. I'll talk about that in a minute. But the better than the full field optimum, we're getting down to where you're still not making as much, but you're still doing okay with the actual. In terms of the organic, you're not doing nearly as well. So you're actually the inefficiency of nitrogen use, because interestingly, because there's no nitrogen applied in the system, it just will outperform in this basis. Excuse me. Site-specific optimum minus the zero rate, of course, this is the average probability of less or equal nitrogen applied. So this is how much nitrogen gets applied. We don't put any on. We don't get any advantage from that. If we have the farmer selected, it'll be greater than or equal to the site-specific optimum. Will it be equal to or less than or equal to the farmer's selected optimum? That's kind of hard to read because it's vertical. And you can see the probabilities are pretty high, 70% chance. Those are pretty good odds. Site-specific optimum being better than the full field optimum, not as high, but still generally fairly up there, kind of in the medium. And what this is really demonstrating that is in these wheat systems, the full field optimum or uniform optimum is pretty much as good as the site-specific in many, many cases. But we wouldn't know that unless we did the experiment. Keep that in mind. We still have to do the experiment to get there. So these are important comparisons to make. And then the actual, and then the organic again. So finally, we get to the total cost of nitrogen used in efficiency across fields in each weather condition. This represents the total amount of money that would potentially be lost by farmers on a field basis if they were penalized for inefficiency. And what we're thinking here is, this is policy information. This is the kind of information that if you really want to, or we as a society want to reduce nitrogen amounts that we're putting into the system, then we should probably be paying farmers on this sort of basis. And if we can produce the information site specifically, we could say, how much on average should we be paying that farmer given their kinds of responses if they've been doing the experimentation? Does that make sense? Kind of? There's a cost. That's all there is to it. So anyway, that's sort of the point. In summary, field-specific precision experimentation creates the data required for adaptive management decision support. Integrating the farmer into the experimental treatment selection is first important step in decision support system development. Repeating experiments in a field provides assessment of variability due to weather and the basis of simulating potential outcomes and the range of outcomes. A set of alternative management approaches assessed. Probability of outcomes helps clarify uncertainty in recommendation decision support. And nitrogen management can be optimized to maximize profit and reduce pollution. So we've demonstrated those things. It's true that we took a whole lot more data gathering and effort to get that cost, or that pollution cost of nitrogen. But what we need to do now is really develop the surrogate measures so we can get at how much is in the plant, how much is in the soil, how much are we losing in the system. So we have the data sets to do it. We just need to move in that direction. Okay, I'll stop there. Am I okay for time? Questions?
Any questions?
Excuse me, this is Chuck. So, are we saying that the yield curves in all cases are flatter than published data from 50 years ago or whatever?
Yes.
And that, yeah.
I mean, they're flatter because we're considering the variation across the field, and they're flatter because of the variation over time. So we have these incredible scatters that we actually didn't anticipate. I mean, you look at a wheat field and you say, man, that looks just like a carpet. It's uniform with good weed control. You can't imagine that there's that variation that there actually is. So spatial variation is real. Equally surprising is from year to year, there's a lot of variation. And this won't surprise you, Chuck, but I think that's something that we don't really take into account. And everybody's always just kind of on this gamble. Let's just use an average response. And that's why when they set their rate, it's not performing as well as it could be.
On my farm, I think that we are living or have been living off of fertilizer practices in the 80s and early 90s, where we used anhydrous ammonia and put on more nitrogen than we used. In our probes, in our soil tests, we found a nitrogen bulge at 2 and 3 feet, and I'm wondering if, Dr. Maxwell, you and I have talked about artifacts a lot, and it's a real headache, but I think that nitrogen bulge is an artifact that maybe is skewing these yield versus nitrogen to be flatter. Just my thought.
I think that's definitely true on your fields, and I think many fields. You're right. We're seeing that we've created a surplus in that profile. The interesting part is that surplus is probably moving down a bit, and it's only the wet years that we get a root system that can get to it. So it does foul the data in some ways, perhaps for a long-term sense of where we're getting that. But what it also does is afford us the possibility of mining that as we move through time. And I think, Chuck, you experimented with this where all of a sudden a couple of years ago, you set your farmer selected rate was quite low, and we questioned you on that, and you said, well, I think I've got it. It's just down there. I'm going to try to mine it. Is that true?
That is true, and I think SRE 1314 shows that. Yeah. In the first year. So this is a little bit tangential, but there's discussion about biologicals and about the regenerative ag and reducing phosphate and other levels significantly, and seeing increased or seeing the yields not fall off. And I just think that the discussion we just had about why my yield curves are flat is going to play into that whole regenerative ag thing. I think But with phosphate and other things, we're living off past experiences, at least for the first few years.
Good point. And I think that, and it's funny because you know, I've teased you in the past about the fact that you're the outlier. And we're always worried about grouping your farm with other farms but mostly because actually you've probably flattened the curve. That's not necessarily a bad thing. It's actually a good thing. You're probably responding to all the experimentation that you've done. But it is different from other farms. As you know, we've worked on your farm for far longer than any others. It goes back to the 1990s, really, where we were working on weed management, site-specific weed management. But when we moved on to some other farms, we started seeing the pattern more of what we expected. And so, granted, you're kind of a special situation there, but we so much appreciate your participation and have for a long time. And certainly the knowledge you bring to the system. Any other questions? Yeah. So Chuck, what we're hearing is that there's all these things that look real uniform to us, but when you get to the Palouse where you have all these hills, it hits you in the face that there can be a lot of heterogeneity. And in fact, with it having such an effect on those hills from the north side to the south side and how soil moves off of those, et cetera, and varies a lot. So thanks for that. Appreciate that.
So Bruce, can you go back to one slide where you talk about cost?
Yeah.
So the cost, so that's average cost per year. You include the cost of technology, like what if the farmer who wants to work on this does not have yield monitor, does not have a protein monitor? Did you include that cost and also the subscription cost to the services?
No.
Okay.
I mean, there's a cost whenever we go from so with the farmer selected, there's no cost. I mean, we're just assuming that there's no technology cost with that relative to the site specific and anything driven by our experimental data from that field. We charge ourselves a $4 per acre amount for that.
Okay. So,
but otherwise, no. And it's certainly when it comes to coming up with the nitrogen, inefficiency measure, that would be highly expensive based on the method that we used. But, we think there's surrogate variables out there for us discovering exactly where that nitrogen is so that we can do this simplified approach to saying, is the nitrogen getting into the plant or not? And the assumption is if it's not, it's polluting. I'm kind of alluding to that. That's kind of an unfair assumption in many ways. As Chuck pointed out, his is still there, ready to be mined if he can get to it with his root system. So most of our soils in Montana will hold on to the nitrogen. In fact, so well that we're acidifying a lot of our soils. So we've got another problem that's coming up with that. So anyway, I think I'm getting at your question, but in terms of the costs to be able to get to these amounts is right now is really high, of course, because you need a graduate student that's going to spend 2 years doing lots of soil sampling, tissue sampling, etc.
yeah, so what I was wondering, basically, so in other words, is the fixed cost versus variable cost and total cost. So did you only include variable cost when you made this calculation for the cost of doing this?
No, there's fixed costs there as well. Yeah.
Okay.
Yeah.
And the $4 average, was that based on service cost, average locally service cost?
$4.
You mentioned $4 per acre. That was what you used
that
for calculation.
$4 per acre is the technology cost to get the experimental data that allows us to come up with a yield and protein response to nitrogen. Okay, so that's information from one consultant. We've had others say that no, it's more like $8. So if they were going to charge somebody to get that data or take their data off of their yield monitor and do something with it, try to make predictions, that's what they would charge. They're
I
not
see.
using our approach necessarily.
I see.
Probably would be more.
Any other questions?
I'd like to address that last question a little bit. We farmers, half the money that we spend, or maybe more, on technology is just to steer straight. And so the variable rate part is not a huge addition to what we buy just to steer straight.
Good point.
Okay, I actually have a question. It's a bit of a projection, and so just like a thought experiment. So, as working in kind of soil health and with a lot of the folks who are interested in regenerative agriculture direction, I'm interested in some of the applications beyond nitrogen. So, and recognizing that you're not a microbiologist or that sort of thing, but so if we put down biological stimulants, like, is there utility in variable rate applying those? That's something that like my brain's been thinking about. So I don't know if you can project out based on the work you've done.
I think absolutely. I mean, I'd be shocked if it wasn't of value. That variability comes from lots of different factors. A microbial community in the soil. I mean, we know when we've taken soil samples, and it's one of the things that's kind of discouraging about using soil information, is that you take a sample here and you move a foot away and take another sample. And if you actually analyze those separately, you find out that, wow, they're wildly different. Even in this uniform condition that we've worked pretty hard to make uniform, that kind of thing happens. So I think that many things that we would do could be placed in the field. So another graduate student of mine, Hannah Duff, is doing, for example, she is looking for areas of fields that, based on yield monitors, have been consistently low yielding. And in fact, with inputs going across those, they lose money. She's promoting the idea that we should take those out of production, turn those into native species, and then she's quantifying what the effect of that is, both in that area and what the cost is, but also, is there any benefit outside of that? And she's actually discovering surprising benefits. There is a number of beneficial ecosystem services that come from even that small ecosystem. Highly dependent upon the age. The longer they've been in, the better they do. But there's advantages from insect management, insect pest management, from weed seed predation. All these kinds of things are actually pays off. She has these shocking curves. I accused her of messing something up at first because I couldn't believe that the yield went up as you approach these edges of those refugia, we call them, ecological refugia in the field. But again, that's kind of the idea there is that, we kind of got onto this because Pheasants Forever was all about this concept. And the fact is there's another income for a farmer to lease fields for bird hunting. And because those places can harbor those birds, it's a great, it's another source of income that in diversifying their portfolio, I guess, of possibilities. That's the issue. But, I was surprised, and Stan, you might have been at that one meeting where I said, nobody's going to want to do this because they don't want to drive around these things. And farmers said, hey, I've got to drive around rock piles and stuff all the time. It's not a big deal for me. So I was actually surprised by that. And it, I think it did make people think that there might be value. So anyway, that's another piece of a pie, but where we use this kind of information to understand those systems. Other question? Was I really that short?
Any other questions? No, I wasn't really.
This is a record.
Yeah, so you got more time.
I'm taking.
Yeah, you're taking David's time.
Okay.
So, but I just want to follow up to the question that Carol was just asking. So what we're presenting in this workshop is the methodology for research, right? So although we're using nitrogen as example, we have been working on nitrogen using this methodology does not mean it only applies to nitrogen research, right? You could easily tweak it a little bit to work on, say, biostimulant, other nutrients, weed management, and things like that, right? Sometimes it could be an easy tweak for the method. Sometimes maybe even a little more complicated, but I think if we sit down and listen to your need, what your goal is, and then so that we can work out a trick of design and make it work. So that's what you were looking for, right? So if, yeah. Yeah, I hear that about stimulants and also, micronutrients and things like that. Yeah.
Yeah, I think one of the things that I've also found really interesting about causes of those some of the spatial variability right within fields are those long-term legacy effects, where there's a good chance we're looking at a bison wallow in a point. There's a good point. That Chuck has got a great example of where there was a corral. I don't know, 80 or 90 years ago, in one part of his field, and it just stands out in the NDVI pictures that here's this square out there that's oddly placed, and it's probably just was a buildup of manure that now has that legacy in that soil. Yeah, right. And part of that is it was deep soil because we had soil erosion. Yeah. No, all kinds of interesting things start to emerge in these fields, and that demonstrate the legacy. And that's certainly a complication of and adding to that variation, that now we just say that's variation. And it comes back to that point, though, of really being careful about quantifying our uncertainty of outcomes. And that's why we've gone to this idea that rather than a recommendation being, well, put on average, this works really well, put on this amount. That's where that was the end point of our challenge. And it worked well when we, as scientists, agronomic scientists, to be more certain, we just added more on. We suppressed that variation. It worked well. As we try to withdraw on some of those inputs, now we really have to be careful about being very clear about what the uncertainty is that we're creating by doing that, by reducing those rates, and how much we accomplish around that. Just the variation you're seeing in these numbers is enough to make you convinced, I think, that wow, that there's a big variance there in what's going on. But I think, and as David said, I joked with Chuck in particular that we try to make him a better gambler, and trying to tell him when it would have been better for him to take his money and go to Lucky Lil's, the casino. But anyway, those are kind of the ways that we're approaching this, is to understand what that uncertainty is and deliver that in our recommendations as, here's the chance you're going to get the outcome that of a better net return. Yeah, just as a little introduction, Sasha's interesting because he is both a scientist and a farmer. And he has been involved with this experimentation with us and came to my lab as a student. But I think I asked him to say, put your farmer hat on mostly and say, what are the challenges to doing this stuff from his perspective? So I won't steal any more of his thunder.